when a caterpillar metamorphoses into a butterfly, it more or less turns itself into soup inside and then starts again. So it's not a macromutational state. You don't have to talk about a macromutational step.
No.
You can, but I mean, there is still a sort of bit of a problem in explaining how I suppose ancestrally, it must have been a much more smooth affair, and the sort of sharp discontinuity between larva and adult must have kind of gradually, there must have been a sort of divergence between the larval form and the adult form. As you say, it's the same genome, and presumably nowadays with homeotic genes and so on, we now would think that the same genes are probably doing similar jobs in the caterpillar and in the butterfly, but nevertheless different as well, because it's a very, very different kind of animal. I mean, the caterpillar is a kind of worm, and the butterfly is something very different.
Yeah, and so what we kind of imagine is, if you look at developing caterpillars now, typically they'll go through several instars where what you're doing is just switching from a small caterpillar to a medium-sized caterpillar to a bigger caterpillar, and then finally you get the big switch to the pupa and the adult. And you could imagine that what we're looking at is a phenomenon where initially it was a matter of growth, that you've got instars, different stages in development, but then what we need to explain is that there must have been some kind of environmental influence, some kind of ecological effect that imposed different selection pressures on one particular stage. And that there have to be mechanisms, again, maybe relating to what we were talking about the other day with the evolution of evolvability, there have to be mechanisms in place that allow a particular stage to be insulated from another, so that you can have molecular changes going on that will allow previous stages to retain their original character, but allow you to add new features to that final stage.
Yes. I mean, there are some marine larvae, mollusk larvae, echinoderm larvae, and annelid larvae, in which the larva and the adult kind of coexist. I mean, the larva swims around. That's its ecological state. It swims around in the plankton, and then when it's time to change to an adult, it doesn't actually change itself into the adult. It simply grows an adult while still retaining. A miniature adult while still retaining its own form. Caterpillars don't do that, but it's another way of doing it.
Yes, and a colleague of mine at the University of Minnesota, Morris, works on parasitic mites, for instance, and until I talked to her, I had no idea how complicated their life histories were. They go through all kinds of different stages with, they've got, in one stage they're parasitic, in another they're living on debris in the muck on the bottom of the stream, and another they're living on dragonflies, and it's just change after change after change. And there's been many, many different processes then that have been selected in that particular lineage.
I think it was George Williams who made the point that parasites with such multifarious life histories can be expected to have really complicated genomes, because they are sort of 5 different animals in one.
Yes.
All coped with the same genome.
Right. But again, they're using the same genes. What's different is the switches that are regulating each of those genes.
Yes.
And that's another thing you'll find in Evo Devo is a great deal of emphasis on the regulation of genes. That many of us think the most exciting things that happen in evolution are not changes within the structural gene itself or the enzyme. It's within those little switches that precede it that will flick it on and off.
And that, of course, explains why essentially all mammals have the same size genome, because what they've got is the same repertoire of, what should we call them, embryological subroutines. And these subroutines are, the master program, just like a computer program, switches on, calls this subroutine, then that one, then that one, then back to that one, and then that one. And the difference between a mouse and an elephant is the order in which the subroutines are called. Whereas the subroutines themselves, they're not the same, but they're not nearly as different as you think they ought to be when you compare a mouse to an elephant.
Yes. So that's what Sean Carroll calls a metazoan toolbox.
Exactly.
That animals have. We evolved all these genes very, very early, and they're initially used on. Many of them were used in things like single-celled organisms, like receptor tyrosine kinases they're finding in quinoflagellates, which are single-celled organisms, but these were thought to be characteristic of multicellular animals. And they were using them for cell-cell associations as little colonial groups or whatever. So all this toolbox built up early, and then what's happened is there's been an elaboration of the usage of the tools during embryonic development.
It looks to me as though embryology, at least in this sense, is becoming exciting in the same kind of way as genetics was exciting in the immediate post-Watson-Crick era when Watson and Crick destroyed vitalism and turned genetics into information technology. It's just a branch of computer science. And it looks to me as though embryology is going the same way, at a rather more complicated level.
Yes, I think it's completely analogous. You know, what Watson and Crick did is they discovered this foundation, and then you could start talking about a genetic code, and you could talk about sequences, and you can ask what's the information there. And this is saying there's another layer on top of that. There's a control layer that's regulating the expression of these genes, and we're trying to decipher how that's done. And contrary to what Goldschmidt ever thought, we're not finding a simple regulator. What we're finding is each gene has its own unique little combination. It's all been sort of patched together by evolutionary history, step by step. And it's very kludgy and clumsy all over the place. And that makes it hard. There's not a lot of elegance there.
Well, that's what you'd expect.